Now we're going to move from mirrors to lenses, from spherical mirrors to spherical lenses. In particular, we call these thin lenses because they're thin. But there are two types of lenses that we're going to deal with, and these are the most common types of lenses. The first is called a convex lens. This is also called a converging lens. You might hear it called that. If you're really comparing lenses to mirrors, this is really more like the concave mirror. So I'm going to write that as a little note over here. So this is sort of similar to the concave mirror in the way that it causes the light to bend. So we'll see that when we're doing ray tracing diagrams that it's very similar in the types of images that it makes. And it's really more like the concave mirror. So be careful with the naming of these because it can get a little confusing because you might think that, well, they're switched. This other type of lens is called a concave. Hold on just a second. Okay, sorry about that. This other type of lens is called a concave lens. And you might also hear this called a diverging lens. So in a similar way, this is really like the convex mirror. Or you can think of that the convex mirror is a diverging mirror. So remember, this was the convex mirror, and when you had rays that were incident on the mirror, the rays were divergent, or they diverged. And so the concave lens is also a diverging lens, though it's more like the convex mirror. So I'm going to write that over here. It's sort of similar to the convex mirror. And that might help you as we go through the ray diagrams to remember that these produce very similar images. There are other types of lenses. I show them here. They're used for various things, various types of glasses, cameras, and optical experiments. And they have different shapes. Most of them are fairly obvious, like this is a plano-convex. It's a plane on one side and convex on the other. Here is a convex concave. So it's convex on this side and concave on this side. This is a similar shape. It's a meniscus, and then this is a plano-concave. So it's concave here, and then planar on this side. We're not going to deal with these, but you just know that they exist. And the focal length is going to be defined in very much the same way as for the mirror. It is 1/2 of the radius of the sphere. From which the lens was cut. Obviously, they're not really cut from a sphere, but if you want to think of this in the same way that we did with mirrors, that we have this big ball, and then we just slice off a piece of it, and that piece becomes our spherical mirror, you can think about it in a similar way. Although with spherical lenses, instead of just having one spherical surface, you have two spherical surfaces. So you can think of it in this way. This is how a convex lens is constructed. In your own mind. It's not actually how a convex lens is made. I mean, these are made by grinding down the glass and then smoothing them. But you can imagine it that if I have these two big spheres of glass and I put them together, and then this place where they come together would be our convex lens. So this shaded portion right here would be our lens. And then we can think about, well, we have a center of curvature here and here, and then we have focal points here and here. And those focal points are half of the center of curvature. Now notice that each side of the lens has a different focal point. Though in this class we'll just deal with lenses that have the same focal length on both sides. And that is just to say that the center of curvature, or just the curvature of both sides, is the same. Both sides, it's like they're cut from the same sphere. But that doesn't have to be the case, and is often not the case in some optical experiments. Okay, and further, we define the focal length based on this geometric idea that it's half of the center of curvature, but just like with mirrors, it can also be the point where parallel rays are focused. So if we were to draw parallel rays here on this converging or convex lens, they would focus at the focal point. And then similarly, if we had rays come in this way, they would focus at the focal point. Now, for diverging lenses, you're going to get a very similar thing, and we had this with the convex mirror. All right, this, however, is the concave lens. I always remember it because it sort of caves in right here, kind of like the concave mirror did. But remember, this is different from the concave mirror in the way that it acts towards light. So here, if we have rays that come in parallel to the axis, they're going to act such, they diverge on this side, but they're going to diverge in such a way such that if you were to trace them back, they would go through the focal point. And so the virtual rays will focus at the focal point for this diverging or concave lens. Remember, the diverging lens is a concave lens, and the converging lens is a convex lens. Further, our magnification is defined the same way. It's going to be negative of the image distance over the object distance, but also remember we also define our magnification based on the image height and the object height. And all those same things will come into play here. And actually, I think this is the same as what we had before, that if our magnification is greater than 1, it's a bigger image, less than 1, a smaller image, equal to 1, same size image. If the magnification is positive, it's upright. If it's negative, it's inverted. And if it's inverted, that means also that our image height is also negative, which would cause this value to be negative. And then finally, the lens equation. And the lens equation looks just like the mirror equation, 1 over P plus 1 over Q equals 1 over F. And it works very much in the same way. However, the sign conventions are a little bit different. All right, so for our object distance, if the object is in front of the lens, then the object distance is positive. If it's in back of the lens, it's negative. Now, what I mean by in front of or back of is that the direction from which the rays are coming. So in this case, our object would be in front of the lens, and the rays are traveling in this direction. However, if we had a situation where the rays were still traveling in this direction, but instead our object was on the back of the lens, like over here, so this would be our object, then we would have a negative object distance. This only occurs in combinations of lenses, and we'll see that in a little bit when we get into combinations of lenses, or if you're in the lab, you probably had this scenario come up. Now, where this is different, that's the same as for mirrors, by the way. Where it is different is in the image distance, because a real image for a lens is going to be formed on the opposite side of the object. So if our image is in back of the lens, that means it's going to be a real image. So for example, here I would have a real image, and it's on the back side of the lens, meaning the side opposite from which the rays are coming. The rays are moving from left to right here in this scenario, and that means that, and then the image is formed on this side. That means that it's a real image. I can physically put a screen right here and project that image onto the screen. However, if the image is in front of the lens, that means that it is a virtual image. So we'll see some scenarios where the image will be over here. And in this case, this would be a virtual image. All right, and then finally, one last thing before we take a few quick test questions, and then we'll do ray diagrams, is that the focal length for convex lenses is positive. Just to remind you, convex lenses look like this, and the focal length for concave lenses is negative. And these lenses look like that. All right, those are converging and diverging lenses. We'll pick up with ray diagrams next.